All right. Good morning, everybody. Welcome back to Data 100, lecture number 14. Today we're going to be continuing our Foundations of Inference lecture from yesterday, and we're going to be talking about risk and loss functions. So as an announcement, I did not record the screencast from yesterday, sadly. I did post a link to last semester's screencast, and I did remember to record the thing this morning, so hopefully we'll get a screencast from today and from now. I do want to repeat for the record that the class is now harder if you don't have a stats background, because the first half of the class is very programming heavy, and the second half of the class, starting today, will be very statistics heavy. And so if you don't have as much statistics background as you do programming background, you should expect to spend more time and more effort learning the concepts that we're going to cover from this point forward. I do want to also point out that in the first half of the class, the main way you get practice with the concepts is through lab, but in the second half of the class, the main way you get practice is through discussion. Okay, so we have a mid-semester survey. It's on Piazza, and it's due at 11:59 p.m. tonight. If 90% of the class fills it out, then everyone gets 0.5 points added back to the midterm. We only have 56 responses, and I believe we need 107 or so to get 90% for the 90% cutoff. So if you haven't filled it out, or you know people that haven't filled it out, tell them to fill it out. Okay. I am going to update some of the due dates for homework. So I'm pushing back the due date for homework 4 to Tuesday, and pushing back the due date for homework 5 to Friday. Originally, homework 4 was due tomorrow, homework 5 was due Tuesday, but I decided to push it back a bit, not only to match the lecture schedule a bit closer, but also because it felt kind of wrong, morally wrong in some way, to give you homework due the week of a midterm. So homework 4 due Tuesday, but do try to get started on it early, and then homework 5 will be due Friday. When's project 2 going to be released? It will probably be released right after. We either have one, I think we have one more homework, because we have homework 6, and then project 2 will be released. I believe we're planning it to be the Tuesday after homework 5 is due. So it'll be due in what is that? That's 2 weeks? 2 weeks from today? Yeah. Okay. All right. Let's talk about risk. So yesterday we talked about how an estimator is a numeric summary of a sample. We saw how an estimator can be the mean of the sample values. It can be the maximum of the sample values. It can be the first 2 values added together and divided by 2. There's a lot of ways to create an estimator, and because of that, we wanted some way to evaluate whether an estimator was good or not. We noted that if a sample was collected randomly, then we can think of an estimator as a random variable. This means that if the individual points in our samples are random, if you treat them as random variables, then the estimator, which is created using the points in our sample, is also a random variable. In other words, if my sample is randomly collected, the mean of my sample is also going to be a random variable. Okay. And we talked about looking at the bias and variance of an estimator. We saw that if the bias of the estimator is 0, then the estimator is accurate, which means that it will get the right value on average. It will not on average, it'll get the population parameter that we're interested in. If the variance of an estimator is low, that means that the estimator is precise. Okay, so precise means that most of the time the estimator will get values that won't deviate too much from its average. I have here an analogy to try to help you understand. As with all analogies, there's some limitations on how far you can push it, but I'm just trying to give you an intuitive feeling for what an estimator is, what bias and variance are. Okay, so the question here is that if I have an archer and she hits the bullseye on one shot, would we say that the archer is good? Well, maybe, but maybe not, because maybe the archer just got lucky on that one time. So what we're really interested in to tell whether an archer is good or not is if he or she can hit the bullseye every single time, or at least most of the time, on repeated attempts. Okay, so if we let our archer be our estimator, and we're interested in how good our archer is or how good an estimator is, If we collect a sample of shots, we can consider that our sample data. Our arrow in the target is our estimate, which is collecting one sample and taking the estimator for that particular sample. And the bullseye is the parameter theta star. Okay. Now, I want to point out to you some notational differences here. So first of all, when I use capital letters, I usually use capital letters to refer to random variables. Okay, so this x sub 1 here is a random variable. And this random variable is saying this is the value for the first point in my sample. Okay, it's a random variable, which means if I go back to my population and collect more data, this x sub 1 will change. When I write little x sub 1, this right here is referring to the point in a particular sample. Okay, so I'm not going back to my population and collecting a bunch of samples. This x sub 1 through x sub n here is one sample that I've collected with n points in it. Okay, a single sample. It's not random, because I've already collected it. Okay, now when I write estimate here, I'm saying, let's say that the estimator is the mean, right? So if the estimator is the mean, then I could write the estimator as capital X sub 1 plus the sum of x sub 1 through x sub n divided by n. And that would be the estimator, because the estimator is a random variable. It's composed of random variables. The estimate, on the other hand, is a single sample mean. Okay, so it's if I collect one sample and take the mean of that one sample, then this right here I would call the estimate. Okay, so confusingly enough, most people, and myself included, will use the same Greek letter for both estimator and estimate. The way you tell the difference is if you use capital X's or lowercase x's. So if you see me write theta hat equal to capital X1 plus capital X2, that you should think to yourself, okay, this is an estimator, it's random. If I write theta hat equal to lowercase x1 plus lowercase x2, you should think, okay, this is a single point, it's an estimate. Okay, and the parameter will always be theta star. So if the bias is 0, that means that the expected value of my estimator is the same as my parameter, which in other words means that the archer's shots will be centered at the bullseye. Okay, so the archer might fire their shots everywhere, but on average, the cloud of shots will be centered at the bullseye of my target. If the variance of my archer is low, that means that my archer's shots will land close together. Okay, so if my bias is non-zero, but my variance is very low, you can imagine a bullseye or a target, and all the points fall in like one spot, but that one spot is not necessarily the bullseye. Okay, so different ways of measuring. I'm trying to get you to imagine with me like bias and variance. Yeah, Danny?
I'm confused for a quick second. We already have the parameter. Why are we even using estimator?
So Danny is saying if we already have the parameter, why are we using the estimator? If you know the parameter, there's no need to do any of this. So if you know the parameters for everything, you can like leave the field of statistics and never come back because you don't need statistics anymore. But most of the time, we don't know the parameter. So in this case, I happen to know that like the center of my target is the bullseye, but in reality, you won't know the parameter. You won't know the average heights of everyone in data 100. You won't know like I don't know, like you won't know how many steps people walked in Berkeley today unless you actually go to each person in Berkeley and count their steps. So like 99.99% of the time in real life, you have no idea what theta star is, and you have to estimate it with a sample. Does that answer your question?
Yeah, but in the bias equation, don't we like subtract off the parameters from our estimator?
Yeah, so Danny says in the bias equation, we make use of theta star. Isn't that kind of weird because we don't know what theta star is? So what we're saying with the bias equation is, what we use the bias equation for is sometimes we do know what the parameter is or will be, and we can use the bias equation to tell us how off we'll be. But other times we don't know. Yeah. And usually what happens here is this parameter is a parameter of a random variable. So for example, you can imagine p in the binomial random variable, or mu in the normal random variable. And so we can find out if our data were collected from a normal distribution, whether we would get back mu of the normal distribution or not, or whether we would get something that's a little off. It turns out that, for example, for the normal distribution, you have two parameters. You have mu and sigma squared, if you remember from yesterday. Okay, so mu and sigma squared. And it turns out that estimating sigma squared is pretty hard. So if you like try out a bunch of things, if you try out different ideas for estimators for sigma squared, you'll find that most of them have some bias. And you'll do that by saying like, okay, if I use this estimator and assume that my data come from a normal distribution, how far off will I be? Okay, so how do we pick an estimator? Well, if we happen to know the distribution of our data, or we make some assumptions about the distribution of our data, then what we can do is find the bias of different estimators. So I have here like theta hat 1, theta hat 2, theta hat 3, theta hat 4. And I'm saying that all of these here are estimators. Okay, and I can find the bias of each one. So some estimators will undershoot, so they'll get a bias, they'll get a negative bias. Some estimators will overshoot, so they'll have a positive bias. And some estimators will get right on the money. Okay, so those estimators we would say are unbiased. But it turns out that there are usually a lot of estimators with zero bias. So, for example, if I look at the normal distribution, I can look at the average of the first 2 values, which is unbiased. The average of the first 3 values is also unbiased. The average of the first 10 values is also unbiased for a normal distribution. So all of those guys are unbiased, and you should be able to figure out or go through the process of showing that they're unbiased by using the bias formula, or going through the expectation of those estimators. Okay, so usually there are many estimators that are unbiased, and so to compare estimators that are unbiased, we add another dimension. We can compare estimators using variance. So here I have theta 1, theta 2, theta 3, theta 4. But once I look at the variance of each estimator, I see that theta 3 has a lower variance than theta 2. So in this case, I would say to myself, okay, theta 3 seems pretty good. It has both lower bias than everyone else and lower variance than everyone else. This is like our optimal estimator. Okay. Now you can also imagine cases where you have estimators that are a little bit biased and have lower variance than others. So for example, if you have theta 4, you might say to yourself, okay, well this is biased maybe a little bit, but it has much lower variance than theta 3. Is there a way I can compare theta 3 and theta 4? It turns out there is. And the way we do this is through what we call statistical risk. Okay, so the idea behind statistical risk is that if you want to pick the best estimator, you want to somehow combine bias and variance in a meaningful way so that you can figure out which estimator is overall like the one that will give you the best results. Okay. So I'm going to define what we call statistical loss. If you let x be the random variable drawn from the population, and let theta be the estimate for the population mean theta star, or any population parameter really, theta star. In this case, I'm saying that theta is an estimate, not an estimator, so it's a single value. Then the squared error loss of theta is this formula here. Okay. And so it's a random variable because it involves a random variable x, and it has higher values when your estimate is wrong, right? So you can imagine here, if theta is 10, and I pick a value from the population, and my value happens to be 10, then we'll do 10 minus 10, which is 0. 0 squared is 0, you have 0 loss. But if I estimate 10, and I actually draw 100, then I'm going to do 100 minus 10 squared, which is a really big number. Okay, so the more wrong I am, the higher my loss will be. It's a measure of how wrong my estimate is. Okay, and keep in mind here that this x is drawn from the population. So this is saying if I reach back into my population and pick out one more individual, I can compute the loss when I go through that random process of picking out one more individual. And because loss is a random variable, we can find its expectation. Okay, so it's meaningful to say, okay, I have here my loss, and my loss tells me how wrong I am for a single point from my population, but I want to know how wrong I am on average. The average loss is what we call the risk, the statistical risk. It's the expected loss over all points in the population. So again, x is a random variable drawn from the population, theta is an estimate, and the statistical risk is the expected value of the loss on my previous slide. And in this case, I've just substituted in the equation for loss into the expectation here. And you should read this as kind of like an oracle. Okay, so you give it an estimate, and the risk will tell you how good it is. And it will tell you how good it is by looking at all the possible points in your population. So it will say, okay, if I think that people walk on average like 1,000 steps today in Berkeley, then I can, if I were able to calculate the risk, I could ask my risk, well, how good is my estimate of 1,000 steps on average? And the risk would tell me, okay, well, it looks like on average you'll be off by maybe like 100 steps. So the risk gives you a measure of how good an estimate is. And as with loss, lower risk is better. So if your estimates are always accurate, like on the money, then your risk will be 0. If your estimates are very far off, your risk will be very high. Okay. Now it turns out that this risk factors both bias and variance into a single measure of goodness. Okay, so if I write down the equation for risk and do a bunch of algebra, which you should be able to do what I'm omitting today for brevity, then you can get the equation on the bottom. Okay, so it looks more complicated, but you can interpret the first part of the equation. So this term right here, the expectation of x is the average of my population. Because x comes from the population, it's a single value from the population, and so the expectation of x is the mean of my population. Okay, so the mean of my population minus theta is kind of like a form of bias, right? Because if my theta is exactly the population mean, then this term right here will be 0. This term right here is the variance of x. So if you remember the formula from variance, this right here is exactly the variance of x. So I can rewrite this complicated looking equation here in this form, where the first term is the bias of theta squared, and the second term is the variance of x. And this holds with equality, so you can think of the risk as the bias of theta squared plus the variance of x. In other words, the risk gives us a combined measure of bias and variance. And so what we say in this class, and also generally speaking, the statistically optimal estimator is the one with the lowest risk. So we'll just say, if you can find the estimator with the lowest risk, that's the best one. No more questions asked. So in this case, notice here that in this risk equation, the only thing that we're allowed to change is theta, our estimate. Okay, so this x here we cannot change. It's just a value for a population. I can't really do much to change the value of a population, which means that I can't really do much to change the variance of x. The variance of x is like the inherent variation in my population. So in other words, if I'm trying to estimate how many steps people took to walk to class today, this variance of x here is just the variation in the real number of steps that people took. So let's say that I walked 1,000 steps, Danny walked 2,000, Steph walked like 4,000. The variance of x is just the variance of all those values put together. Okay, the bias of theta, on the other hand, is something that I can change, right? So I cannot change what happened in my population, but I can change my estimate. And I can change my estimate so that the bias is small. Okay, so in other words, to minimize the risk or to make the risk as small as possible, I want to choose theta so that the bias is as small as possible. That's how you pick, in this case, for this example, the best estimator. Now you may notice here that the bias formula is expected value of x minus theta. So if we let theta be the expected value of x, then this term right here goes to 0. Okay, so for this particular case, if I'm trying to estimate the mean of a population, what I would like to do is just say, okay, I'm trying to estimate the mean of my population. the best estimator I can do is the expected value of x, the expected value of all values from the population. Okay, any questions on this? I'll let you stare at it for like 1 minute. Okay, so there's a problem here. And the problem is that we cannot actually find expected value of x. Why can't we do that? So I want to pick theta so that the expected value of x, I want to pick theta so that theta is the expected value of x. But I am proposing to you that I cannot actually find this value. Why is it hard to find? Why don't you talk it over with your neighbor and see if you can figure out why it's hard? Go ahead. All right, any ideas? Why is expected value of x hard to find? Any guesses? Hypotheses? I'll wait for one volunteer. Yes, name and answer.
Name is Pranav.
Pranav. Hi, Pranav.
And I think it's hard because if you look at the formula of expected value, you have this term where you have to know the probability of the nine variables taking on the possible values. And then if you know the probability, the original population is prior, then why are you doing statistics?
Yeah, so Pranav says, if I want to find this expectation, I have to know a lot of stuff. Basically, you're saying that I have to know a lot about my population. And in reality, you need to know everything about your population in order to find the expected value of x. Because the expected value of x is the average value, your population parameter. So in other words, I gave you this formula for risk, but it turns out to minimize risk, you need to know your population parameter to begin with. And so it seems kind of circular, but it does give us a way forward because we can estimate expected value of x. Okay, and so the idea here is that we don't know the expected, like if we had the population, we could find the expected value of x by taking the average of all values in the population. We don't have a population, we have a sample, and if our sample is randomly drawn from a population, then we can pretend the sample is a population. Okay, we can let our sample stand in for the population, just as we've done in data 8 many times before. So in data 8, when we did the bootstrap, what we said was, let's pretend that our sample is a population, so we'll simulate taking a bunch of samples from our quote-unquote population. And here we're doing the same principle, and we're saying, okay, well, we cannot find expected value of x if x comes from our population, but let's pretend that x comes from our sample. And if x comes from our sample, then the expected value of x is just the average value of the points in my sample. And this I can calculate because I have a sample. It turns out that this approximation holds as long as we're using a sample that's randomly selected from the population. In this case, I'm saying that we have an SRS. Okay, so we have risk. We're trying to minimize our risk. We're trying to minimize risk by finding the expected value of the values in the population. I can't actually do that, So I'm going to find the expected values of stuff in my sample and claim that the values in my sample look like the values from the population. That's only so that last statement is only true if my sample is randomly selected. Okay, so if I don't have a random sample, then I have no idea whether this is actually a good approximation or not. Okay, so I have here an approximation for expected value of x. So I can plug this approximation back into my risk equation. Okay, so if I plug the approximation back into the risk equation, I get what we call the empirical risk. And we call this the empirical risk because it's based off our sample. In data 8, we talked about the empirical distribution, and the empirical distribution is, again, the distribution of our sample. Okay. So if you see the word empirical, you should think, I'm doing something with my sample. Okay, so what I've done here is I have the exact same equation for risk, but I put hats over everything to denote the fact that we're talking about stuff that's based off our sample instead of stuff that's based off our population. And we have here the empirical risk is equal to the empirical expected value plus the empirical variance. And this equation here is approximately equal to the real statistical risk. Okay, so we have some approximations, but now we actually have something we can minimize, right? So we want to make this guy as small as possible, and the way we set this to be as small as possible is to set theta equal to the mean of our sample. If we set theta equal to the average of our sample, then theta is equal to expected value hat of x, and that means that this bias term will be 0. Okay, so let's retrace. I'm going to retrace quickly the steps, like the high-level steps that we've done so far. So there are a lot of equations and a lot of details, but here are like the main takeaways from each of the slides that we've done. Okay, so first, we got estimators. We're trying to figure out whether an estimator is good. We talked about bias and variance. We said, okay, well, bias and variance are both measures of goodness, but we wanted a way to combine both bias and variance. We talked about risk, and we saw that risk is a way to combine bias and variance. And in fact, risk lets us choose the best estimator if we can find risk. The problem is that risk is hard to find, so instead of finding the real risk, we approximate the risk with the empirical risk. Okay, so all of this is in the hopes that we can make some good estimations about our population, right? So again, I want to tell how many steps people walked in Berkeley today from a sample of people from Berkeley. Okay, so I can't go up to everyone in Berkeley and measure how many steps they walked, but if I take a random sample from the people in Berkeley and measure the steps they walked, using the knowledge of empirical risk, I can say, okay, I'm pretty sure that if I take the average of the number of steps people walked in my sample, I'll be able to get a value that's pretty close to the real number of steps walked by everyone in Berkeley. Okay, so we're doing inference now. We're going from sample back to population. And this equality here relates a quantity in our sample. So these are quantities in our sample to values from our population, the real statistical risk. Okay. So risk combines the bias and variance. And so one other way to think about what risk is measuring is, let's say I have two estimators, theta hat 1 and theta hat 2. Theta hat 1 has no bias, but it has a large variance. So its distribution will look like the red curve right here, whereas theta 2 has a small bias and has a small variance. Okay, so it's a non-zero bias, but it has a small variance. And so it looks like this blue curve over here. So it goes up high and it goes down. And so risk essentially gives you a measure of saying, well, even though the red line is unbiased, the variance is too high, so that's not as useful to me as this blue curve over here. Okay. It turns out that for a lot of real-world quantities, you won't be able to find an unbiased estimator. So really, like, risk comes into play quite often and more often than you expect. In this class, most of the time we'll have unbiased estimators, so you don't have to worry about, we won't have to worry about that too much, but you should keep this in mind because risk is kind of like the, what is it? It's kind of like the statistics approved way of picking an estimator. Okay, so let me go over all the notation that we've done so far. So, theta hat refers to a parameter about the population, or theta star, sorry. You'll see me also plug in actual parameters into instead of theta. So you might see me use mu star or sigma squared star. This sigma squared star right here refers to the variance of my population. This mu star right here usually refers to the mean or average value of my population. And I use theta star so you can just know that I can replace theta with any one of these variables here. And in reality, there are many more variables, but I'll just use theta as like the catch-all, the parameter that I'm trying to estimate. Okay, if I write theta equal to 1 over n times sum of random variables x sub I through x sub n, this is what we call the estimator. It's a random variable that outputs estimates. If I use little x's instead of big x's, this should tip you off that I'm talking about a single estimate. It's not a random variable, it's a single value based on the sample. And the estimate that minimizes the empirical risk, I'll give it a special name, or I'll use a special notation for it. I'll put a hat on top. Okay, so theta is any estimate if it's based off the sample, and theta hat is kind of like the optimal, empirically optimal estimate. It's the estimate that minimizes the empirical risk. Okay, so it's kind of like I have a bunch of kids, and I have a bunch of kids named theta 1, theta 2, theta 3, and my favorite kid, I'll put a hat on top. And so you can think of this as like the hat being like, this is the best estimator for the empirical risk. Okay. We've gone over a lot of expectations, so let me recap quickly all the expectations that we've done so far in the past 2 lectures. So if x is just any old random variable, the expected value of x we should interpret as the long-run average of that random variable. Okay, this is true for all expectations, but if we change the random variable x, we can interpret the expectation in a different way, all right? So if x is a random variable with a value drawn from the population, then the expected value of x is now the population mean. It's mu star. We give that a special name. Okay, if theta is an estimator, then expected value of theta minus theta star is what we call the bias of theta. Finally, we've talked about how L of theta is a loss function, and if theta is an estimate, then the expected value of my loss is the risk. Okay, so you should read these guys as I'm always taking the expected value of a random variable, but if the random variable is something special, then I get a special output. All right, any questions about this? Okay, let's take a break. Open up the form, and then go back to my slide. We'll come back in 3 minutes. Hey Ray, how's it going? How's it going?
It's going good. It's going good. How are you?
I'm alright.
Alright.
What's up?
I'm just curious about the kind of overlap that the rest of this class will have with, like, I don't know if you're familiar with problem 40 or like 135 here. How much do they overlap?
After today, almost nothing. Yeah.
Okay.
So problem 40 goes like way deeper into random variables and expectation and variance. It goes into like joint distributions.
Yeah.
It goes into continuous
I've taken
distributions.
problem 40.
Oh, you've taken it. Oh, okay. Yeah. So basically, this is all the probability that we'll use in this class. And then after today, we're going to be talking about like modeling almost exclusively.
Cool.
Yeah.
Nice enough. All right. Thank you.
All right, hey, let's bring it back. And I want to talk now more about loss functions. Okay, and the reason why I want to talk about loss functions now is because loss functions are, you could say that loss functions are at the heart of a lot of machine learning techniques. Okay, so a lot of machine learning techniques are, you swap out the loss function, you get a different type of estimation, and you call that something new. So you'll call that like an SVM, or you call that linear regression, or you call it logistic regression. But at the core, a lot of machine learning techniques are this idea of picking the right loss function, setting up your data in the right way, and then just minimizing that loss function until it gets to be as small as possible. Okay. And so what I want to do right now is go through some calculations involving loss functions, and then give you 2 examples of loss functions so you can kind of see the trade-offs between switching between loss functions. Okay, so if you remember, we used loss functions just now when we talked about risk, right? So the risk is expected loss, and right now I'm just focusing on the loss part. So I showed you this equation here, which we call the mean squared error loss. I'm going to call it the MSE loss because the mean squared error is just too long to say. So if I say MSE, or if you see MSE in the book, you should think of it as this is the mean squared error. The reason why we call it the mean squared error is because we have x minus theta, this is the error, and we square it. Okay. Now this loss here depends on x, which is a value from the population. But as with the risk, there's an empirical version of the loss, which we call the average empirical loss, where instead of the capital X here, we substitute in our actual data points, and we take the average loss over all the data points. Okay, so what are we doing here from here to here? We're saying, okay, well, this depends on the population. Instead of calculating the loss on the population, which I don't know how to do, I can find the loss on a particular data set, which I do know how to work with. And this right here says, for every point in my data set, find the error between my estimate and the point, square the error, and then find the average error. Okay. You may notice that this expression here is actually, roughly speaking, the same as the empirical risk. And so you'll find that in the world, more commonly, you'll see people saying minimize the loss function instead of minimizing the empirical risk. But really, those two things are, you can think of them as roughly the same thing. Okay, so they're not exactly the same, but they're close enough that for the rest of this class, I'm going to say average empirical loss, and occasionally I will remind you that we're minimizing the empirical risk, but you can think of these terms roughly interchangeably for the purposes of this class. Okay, so let's take the L. So if you have a sample with 4 points and we have an estimate theta equals 4, calculate now the average loss. And so take out a pencil or like take out your Jupyter notebook and try to find the average loss on this particular data set. And I should clarify here, this is the average MSE loss. MSE. Okay, so this again is something you should be able to do pretty much in your sleep after you've had some practice with loss functions, of course. But to do the average loss, what you do is you write down the equation for loss, plug in the values. So here I have 4 points, so I do 1 over 4. I have 1 minus 4 squared, which is 3 squared, 3 minus 4 squared, which is 1 squared, 5 minus 4, and then 11 minus 4, which is 7 squared. I add them all up, divide by 4, and I get 15. So my loss here is 15, or the MSE loss for this data set is 15. Okay. I do want to point out also this notation that I have here for this function. So this formula here looks relatively complicated. But all I'm saying here is that if you see parameters for a function, you should think to yourself, if I change one of these parameters, I'm going to change my loss. Which kind of intuitively makes sense, because if you change your data set, you'll get a different loss. Or if you change your estimate, you also get a different loss. Okay, so if I write x sub 1, comma, dot, 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 through x sub n, what I'm really saying is the loss here depends on both my estimate and my data set. If I pick a different data set, I'll get a different loss. If I pick a different estimate, I'll also get a different loss. Okay. Now, since we can minimize loss to minimize risk, we can talk about minimizing the loss. Okay, so we can minimize the loss using the same sort of reasoning that we use for minimizing the risk, which is taking kind of eyeballing this equation and then figuring out, okay, what value of theta is the best value of theta to put in here. But the more sophisticated way of minimizing the risk when you can't just eyeball the equation is to use some calculus. Okay, so the idea here is we'll take the loss here and we'll take the derivative with respect to theta and we'll see what value of theta gives me the smallest loss. Okay, so you can imagine with me that if I take different values of theta, so if I try theta equals 3, I'll get a different loss. If I try theta equals 7, I'll get a different loss. And my overall goal is to find the value of theta that gives me the smallest loss overall. Okay? And to find the smallest loss, I can plug numbers in until I find a small number, or I can use calculus to find the right value once and for all. Okay, so what I'm going to show you is calculus to find the minimum loss for our data set. Okay, so I'm going to minimize loss. We happen to know that theta here will be the sample mean. Okay, so what we should find from using calculus is that the best value of theta should be the mean of my points in my sample. Okay, so I'm writing down here the equation for loss, the average mean squared error loss on a data set. I'm going to take the derivative. So this right here is a partial derivative with respect to theta. And what I'm doing here is I'm taking the derivative of this sum here. So the 2 comes down here, and I use a chain rule to multiply by -1. So if you don't remember your calc rules, you should refresh your memory for calc. But this right here is a derivative of the inside part of the summation. And then I'm going to simplify a little bit, so I'm moving the negative 2 out to the outside, and I have here sum of x sub I minus theta, but theta doesn't depend on x sub I. I have n thetas here, so this right here becomes n times theta. Okay. You can also find this out by like writing down the summation, so you can try yourself, like if you expand out the summation, if you're confused by this step here, you can say, okay, what is the summation? The summation is x sub 1 minus theta plus x sub 2 minus theta plus x sub 3 minus theta, and then you can group together the x sub i's, and you can group together the thetas, and you'll find that you get the summation of x sub i's and n theta terms. Okay. So if I set this equation equal to 0, I can find the minimizing value of theta, as we do for derivatives. And in this case, I've set it equal to 0. When I set my loss equal to 0, I'm about to solve for theta, and so I put a hat over the theta to say this is the variable I'm going to solve for, which is going to be the minimizing value of theta. Okay, I can do some algebra, so I'm going to move stuff over to the other side and divide by n, and I'll get theta hat is equal to 1 over n times the sum of x sub I, which doesn't show up properly. It's supposed to be, I believe, bar. It's supposed to be x bar. I apologize. But you can imagine with me here that this right here is x bar instead of x sub I. Okay. So it's good that we have confirmation through calculus that the minimizing theta, minimizing the loss is the same as minimizing the risk, and we get the same result, which is theta hat should be the mean of my sample points. This also intuitively makes sense, right? Because if I go back to my loss equation here, or if I just go back to here, how do I make this value as small as possible? Well, for the mean squared error, I want my theta to be close to the middle of my data points, right? So if my theta is really far away from all my data, then every single term here will be very big. If my theta is very close to most of my points, then most of the terms will be small, and I'll minimize the loss. Okay, so this right here is kind of like the statistical confirmation of our intuition, but really what you want to do is like, you should read the equation, translate it to English, and then you can work through the math and make sure that the result from your math confirms your intuition. Okay, so that's how you make sure you don't get like really weird results when you're doing these derivations. All right. So what I'm going to have you do is replicate the derivation. Okay, so try not to peek at the previous slide, and all I want you to do is practice taking the derivative and going through all the steps. You know what the answer should be, okay, so you should try to aim towards getting the sample mean, but actually going through these steps will be pretty informative for you because I expect you to be able to find the minimizing theta for different loss functions. So if I give you a different function for loss, you should be able to like go through the steps for that particular loss function and find the minimizing value of theta. Okay, so try this out for a few minutes. You know the answer, so don't peek at the answer. Just try to see if you can go through the process of all the steps needed to find the minimizing theta. Go ahead. How many of you are done with this derivation? Only a few. It's not as easy as you think, right? It's like not just taking the derivative. There's like quite a bit of reasoning that has to go into it, which is why I'm making you do it as like a little exercise. Okay, so try it out for like 1 more minute, and then talk it over with your neighbor afterward and try to see if you can, if you get stuck, try to talk with your neighbor and try to see if you can get yourself unstuck. The reason why I'm doing this also is because the skill for recognizing the steps in the derivation is very different than the skill of actually doing the derivation yourself. Okay, so if you actually do this derivation yourself, you'll find that even though all the steps on the previous slide made sense to you, trying to recreate those steps is actually pretty non-trivial, okay, especially if you're doing it for the first time. Okay, so try it out, talk to your neighbor about it, see if you can make some progress. Okay, so I'm going to move on now, but you do have the answer on the previous slide, but you should really practice this until you can do it like without peeking at the answer. If you just write down the equation for loss, you should be able to just like take the derivative, find the minimizing theta, and just do that. Okay? All right. Let me tell you about another loss function, which is called the mean absolute error. So there are actually many other possible loss functions, but today we're only going to be talking about the mean absolute error. It looks a lot like the mean squared error, but instead of squaring the error, we're going to take the absolute value of the error. Okay, so this term right here is what we call the error term. It measures how far off we are, and we can take the absolute value of this error term because sometimes we'll get negative errors and sometimes we'll get positive errors. Okay, so we have here the mean absolute error. It turns out that the minimizing theta for this particular loss function is the sample median. So your exercise now is to prove it. Okay, so I will give you a hint, which is that the partial derivative, there should be an x here. The derivative of the absolute value of x is what we call the sine of x, which is 1 if x is greater than 0, and negative 1 if x is less than 0. Okay, so another exercise for you. If you found the first one too easy, then you should really try your hand at this one. This is a little challenge. Okay, so find the minimizing theta for the mean absolute error loss, and your result should be that theta is the median of my sample. Go ahead. How many of you guys are done? Got a few. All right. Try it out for 1 more minute. It's not an easy derivation, but keep trying. Okay, so why am I making you go through all this work? It's because you should be able to find the minimizing theta for various loss functions. So I can replace this little absolute value here with something different. I can replace it with, I don't know, x minus theta to the 4th power. I can replace it with log ln of absolute, like ln of x minus theta. I can do all sorts of different things with this loss function, and you should be able to find the minimizing theta for various different loss functions. Okay, so the first step here is to write down the loss equation, and then what I do is I split up this formula into 3 parts. So this summation here, I think of it as a 3-part sum. Okay, so I can find all the times where x of I is less than theta, and I'll put that in one sum. I'll find all the times where x of I is equal to theta, put that in the middle sum, and all the times where x of I is greater than theta, I'll put that in the third sum. So you can see here that I have 3 components, but the 3 components sum up to the first sum because I split up my data into 3 partitions. I have one section of my data where all the points are lower than theta, one section where they're all equal, and one section where all my points are greater than theta. Okay, the reason why I do this is because when I take the derivative of this sum right here with respect to theta, this right here becomes -1. And the reason why it becomes -1 is because the slope of the absolute value function below 0 is -1. Right? So the absolute value function looks like a v, right? Like a v. If you have negative values in the absolute value, the slope is -1. If you have positive values in the absolute value, the slope is +1. Okay, so this right here is also the sine function. So I have here, all the points that are below theta will have a slope of -1 once I take that derivative. All the points all the times where my points are equal to theta will have value 0, and then all the times where the points are greater than theta I'm just going to say are 1. Okay, so I'm going to say this is 0, and then when I take the absolute value of positive numbers, the slope of that is 1. Okay. And so this term right here is 0, so I'm going to take it out. And then I can take away the 1 over n because this is equal to 0 here. And what I can do is I end up with this equality where I have here these weird summations. Okay, but these weird summations are for every point in my data that's less than theta, I'm going to have 1, the value 1. This right here says for all the points in my data set that are greater than theta, I'm going to have the value 1. And in order for this derivative to equal to 0, I want the left-hand side to be equal to the right-hand side. Okay, so it looks complicated, but what you want to do, I was supposed to show up one by one, is you want to find theta so that the left-hand side is equal to the right-hand side. And the way you interpret the left-hand side is you say, okay, this right here counts up how many points are lower than theta. Right? So if I have points 1, 2, 3, and then I have theta equals to 5, then this summation over here will be 3, because it will count up the number of points that are below my value theta. The right-hand side does a similar thing. It counts up the number of points that are greater than theta. So if I had a data set 1, 2, 3, and then 10, 11, 12, and I let theta equal to 5, then the left-hand side will be 3, and the right-hand side will also be 3, because it will count up how many points are greater than my estimate theta. Okay. And it turns out that to find the right theta, I want the number of points on the left to be equal to the number of points on the right, which is a definition for the sample median. And so because of that reasoning, I say that theta hat is the median of my sample points, because the median is the point in my data in which the left-hand side, the number of points on the left is equal to the number of points on the right. Okay. That's complicated. So try it out at home. Try to see if you can wrap your mind around all the steps I did here. Okay, but I'll show you a demo because we've been working in Mathland for a little bit. I'm sure by this point, you must be so glad to see Python again. All right, I'm going to zoom in. Okay, so I have here some flight delays. I stole this data set from the Data Yates book. Okay, so I have here the delays for United Airlines in the summer of 2015. And I have here a histogram of all the delays. There are some planes that are delayed by a lot, right? So there are some planes that are like out here that are delayed by, this is in minutes, I believe. So they were delayed by like 10 hours, okay? So sad for you if you're on that flight. This is quite, like the histogram is quite skewed, so I want to zoom into this region over here. So I'm just going to make another histogram with where I'm zooming into the left part of it. So you can see that most of the planes were not delayed. But some of them were delayed by quite a bit. Okay, I can write a function to calculate the mean squared error. Okay, so what I'm doing here is I'm saying I want to estimate the average flight delay. To estimate the average flight delay, I can write the mean squared error. Okay, so if I have theta and I have a series of data points, instead of writing a loop in Python, I can use NumPy array, like arithmetic, right? So I can write np.mean of theta minus my data set squared. And I can return that. And that's the mean squared error. Okay? So if I find the mean squared error of, let's say I think my estimate for the average flight delay is 10. My mean squared error is like 1600. If I try 15 here, I get a lower mean squared error, right? And so basically what I'm saying here is that I want to find the value of theta that minimizes the mean squared error on this particular data set. What I can do is define a function to try out a bunch of different thetas for me. And I can write, let's try values of theta between 0 and 30, and then I will make that data frame with the MSE error. Okay? So I have here a bunch of thetas and the mean squared error for every single theta value. I can actually plot these losses, right? So these are the losses, the average loss for different choices of estimation. I can plot those to show you what that looks like. Someone saved that water bottle. Okay, so I get this plot. Talk with your neighbor for 1 minute. Explain what this plot is showing and why the plot looks like this. Go ahead. All right. So what am I showing on this plot? On my x-axis, I have different estimates, okay? Different estimates. This is saying if I thought that theta should be 10, this is the mean squared error for that theta choice of 10. This is saying if I think that theta is 20, this is my mean squared error for the theta choice of 20. Why does it look like this quadratic looking curve? It looks like that because the mean squared error has a quadratic term in it. So it's a squared error, and because it's a squared error, what you're seeing here is what looks like x squared. Something that looks kind of like x squared. Okay, so this is not the data. These are estimates on the x-axis and average losses for each estimate on the y-axis, but every point here was calculated using my entire data set. Right? So for every choice of theta, I'm going to compare it with every point in my data set and find the average loss. So this is what we call a loss curve. It's a curve of losses for different choices of parameter, or different estimates of a parameter. Okay. Now you'll notice that this loss curve kind of dips down here, and we see here some small mean squared errors in this region here. We can find out what those thetas are by looking at my MSE vals, and I can just sort values by the MSE. Okay, so we see here that on this curve, the theta choice of 17 gives me the smallest mean squared error, but we happen to know that the minimizing value for the mean squared error is the mean of my data set. So I can actually find the exact minimum of this loss by taking the mean. Okay, so it turns out the best value of theta is 16.66, and I can also show you the mean squared error for this value of theta here. So let me save this in a variable, theta hat MSE, and then I'll display theta hat, theta hat MSE, and then MSE like this. Okay, so the best value of theta is this value here, and indeed it turns out that this mean squared error is actually lower than all the other values that I've tried. So this is the best value of theta. And so if I pick the loss function, if I pick the mean squared error loss function, I would say my best estimate is 16.66. Okay, I can compare the mean squared error with the mean absolute error. Implementing the mean absolute error is not too difficult. So again, I'm going to take the mean of the absolute value of theta minus my data. Okay. The mean absolute error for theta equals 10 is 20. And so like with the mean squared error, I can make a data frame with my thetas and this loss function, like so. Okay, so here I'm trying out a bunch of different theta values, and I'm computing the mean absolute error for each one. I can also plot these. So if I write scatter plot, x equals theta, y equals MAE, like so, I get this plot here, which looks kind of like our mean squared error loss curve. But this time I'm swapping out the mean squared error with the mean absolute error. Okay. One thing you may have noticed is that the y-axis here is much smaller. Why is the y-axis much smaller? It's not squared? Right. So the errors are not squared, which means that basically the values will be smaller than before. And you see here that this line is increasing, but it's increasing at roughly a linear rate. Okay, so it's not going up very dramatically like the quadratic was. If I had a quadratic curve here, it would probably curve up right around here and go way above the mean absolute error. Okay. So I can find the minimizing theta for the mean absolute error. It's the median, which we just showed. Okay. here is that theta along with its mean absolute error. Okay. Let me compare the theta for the mean squared error with the theta for the mean absolute error. So we have here two different loss functions, and we have two different estimations that result from picking a different loss function. They're quite different. So why don't you talk over with your neighbor why they're so different and what this means? Okay, so if you told your partner that they're different because we took the mean of one data set and the median of the same data set, and the mean and the median are different, you got maybe like 20% of the way to like a good answer. Okay, so a good answer in this case is saying you want to look at the loss functions. The mean squared error says if I'm off, I'm going to take a large penalty. So in other words, let me plot the data again, or we can just scroll back up here. If I guess the value 50, the mean squared error says that the values in the tail will really hurt me, right? The error for those values will be really high because they'll be squared. And so in this case, what's going to happen is the mean squared error will favor larger values because it's more scared, quote unquote, of larger values. Larger values will result in a really large error. The mean absolute error, on the other hand, says, well, I don't really care about values that are really far away. I'll just say that if you're twice as far away, I'll give you twice the importance. Whereas the mean squared error says, if you're twice as far away from the estimate, I'm going to give you 4 times the importance because of that squared term. And so that intuitively is what the median and the mean are doing. Right? So the mean is affected by outliers, and the median is not so affected by outliers. It's mostly robust to outliers. And one of the reasons why the mean and median are robust to outlier, the mean is not robust and the median is robust, is because they're the minimizing values for 2 different loss functions that have 2 different properties. Okay. So if you ever wondered why in stats we always look at the mean and the median and why we can't just use one, this is kind of like the real underlying reason why we can't just pick one. Sometimes we have different requirements, and sometimes we need different estimates. Okay. So how do you pick a loss function? So if I gave you 3 different loss functions, how would you pick one? The unfortunate answer is that it just depends. It depends on the context, and it depends on the domain that you're working in. Usually the mean squared error and the mean absolute error are the most common. But when if you ever work with neural networks, they use all sorts of weird loss functions there. You'll see the hinge loss. You'll see weird loss functions. Basically, you'll see different ones. The deeper you go into data science, the more loss functions you'll see. And the way you pick a loss function is to understand it. Once you understand it, you can use your domain knowledge to figure out which loss function is most appropriate. For example, the mean squared error has severe penalties for very wrong values because the error is squared, but sometimes this is what you actually want. So for example, if you're in an airport, and if you guess wrong on an airplane delay, then that can have cascading effects for the rest of your day, right? So if you've ever been into an airport and like the first plane of the day is delayed, all the planes are delayed, and then like the last plane of the day is like screwed over. They have like a delay of like 6 hours or something. And so if you're at an airport and you really care about like not getting destroyed by really high delays, then you might want to use the mean squared error. On the other hand, if like your errors are not, like making really bad mistakes is okay as long as you don't make them too often, then you can use the mean absolute error. So it depends on your context. Okay. So in summary, we talked about risk. Risk combines bias and variance. We use empirical risk instead of the real risk because we can actually use the empirical risk. We make estimations by minimizing the loss, and we talked about 2 important loss functions, the mean squared error and the mean absolute error. All right, thanks for coming, and I'll see you on Monday.